What does the future hold, and how do you stay ahead? Artificial intelligence for autonomous vehicles offers a clear-eyed look. We will focus on what it says about autonomous and vehicles. Stay with me, the best part is near the end. Chapter 1: Autonomous and Fatalities. 1. Summary of fatalities due to traffic accidents. Figure primary components in driverless technology. Figure schematic block diagram for autonomous vehicles. Figure autonomous levels. Figure fundamental navigation functions. Figure an insight of a self-driving car. Figure training the model using deep learning techniques. Figure communications between V2V and V2R. Figure automated control system. Figure identification of ambulance locations. Figure alternate routes to reach the target. Chapter 2: Road and Vehicle. 1. Aim of the proposed research. Figure challenges for gesture rule recognition. Figure vehicle features. Figure challenges for vehicle light detection. Figure road markings along the road. Figure road lane marks affected by shadow. Figure road lane marks affected by low illumination. Chapter 3: Image and Detection. 1. Driverless car. Figure flow diagram of ground surface detection. Figure input and the obstacle detection. Figure image processing stage 2. Figure image processing stage 3. Figure image with the car detection. Figure image processing background reduction. Figure final result analysis. Chapter 4: Architecture and Flowchart. 1. Flowchart for the testing phase. Figure different types of facial emotions. Figure segmentation of the facial expression recognizer (FER) method. RESP. Figure pre-processing and extraction/classifier of frame using CNN. Figure system architecture for real emotion recognition using movie clips. Figure collections of grayscale images. Figure CNN architecture. Figure matrix waveform for the sets of 6 global expressions. Chapter 5: Image and Proposed. 1. Input flowchart of the proposed work. Figure input image. Figure sample pre-processed images of NTHU drowsy driver detection dataset. Figure A. Pre-processed image and panels B, C, and D are the figure A. Face image, B. Eye blink, C. Yawning, and D. Head figure output image of histogram of oriented gradients, HOG. Figure graphical representation of the proposed system performance. Figure graphical comparison of the proposed system with dissimilar classif. Chapter 6: Autonomous and Vehicles. 1. The layered architecture of the autonomous vehicle. Figure automated vehicle. Figure automation levels of autonomous cars. Figure threat model, Karthik et al. Figure IoT infrastructure for autonomous vehicles using AI. Figure cyber attack defense mechanisms. 1. Artificial intelligence in autonomous vehicles: a survey of trends and challenges. Uma Maheswari Rajashekaran, A. Malini * and Mahalakshmi Morrigan Garajar College of Engineering, Madurai, India. The potential for connected automated vehicles is multifaceted, and automated advancement deals with more of Internet of Things, IoTs, development enabling artificial intelligence, AI. Early advancements in engineering, electronics, and many other fields have inspired AI. There are several proposals of technologies used in automated vehicles. automated vehicles contribute greatly toward traffic optimization and casualty reduction. In studying vehicle autonomy, there are two categories of development available: high-level system integrations like new energy vehicles and intelligent transportation systems, and the other involves backward subsystem advancement like sensor and information processing systems. The Advanced Driver Assistance System shows results that meet the expectations of real-world problems in vehicle autonomy. Situational intelligence that collects enormous amounts of data is considered for high-definition creation of city maps, land surveying, and quality checking of roads as well. The infotainment system of the transport covers the driver's gesture recognition, language transaction, and perception of the surroundings with the assistance of a camera, light detection and ranging, LiDAR, and radio detection and ranging, radar, along with localization of the objects in the scene. This chapter discusses the history of autonomous vehicles, AV, trending research areas of artificial intelligence technology in AV, state-of-the-art datasets used for AV research, and several machine learning, ML/deep learning, DL, algorithms constituting the functioning of AV as a system, concluding with the challenges and opportunities of AI in AV. Vehicle autonomy, artificial intelligence, situational intelligence, datasets, safety standards, network efficiency, algorithms. Introduction. An autonomous vehicle in simple terms is that its movements are from the start to pre-decided stop in autopilot mode. Autonomous vehicle technology is developed to provide several pros in comparison with human-driven transport. Increased safety on the road is one such potential. Primacy. Connected vehicles could drastically decrease the number of casualties every year. The automated driving software is the most comfortable transport system that highly supports the class of people who could not drive because of age and physical constraints. Autonomous vehicles help them to find new smart ideas, and it is predicted that it could provide them with different opportunities to work in fields that require driving. Automated decisions are taken without any human intervention, and the necessary actions are implemented to ensure stability of the system. The smart connected vehicles are supported by an AI-based self-driving system that responds to external conditions through the ability to sense their surroundings using adaptive driver control, ADC, that uses lasers and radars enabled with ML and DL technologies. To extract object information from noisy sensor data, these components frequently employ machine learning, ML-based algorithms. An understandable representation of autonomous vehicles as a system is shown in figure. The history of driverless cars took the spark from the year 1478 with Da Vinci creating the first driverless automobile prototype. In Da Vinci's vehicle, there was a self-propelled robot that was driven by springs. It had programmable steering and could output predetermined routes. This brief history shows where the roots of artificial intelligence may be found in philosophy, literature, and the human imagination. Autonomous vehicles, AVs, were first conceptualized in the 1930s. It was the Hodina Radio Control Project that demonstrated a radio-controlled driverless car. In the mid-20th century, General Motors took the initiative to develop a concept car called Firebird 2. This was considered the basis for the first cruise control car named Imperial, designed by the Chrysler Company in 1958. Back in the 1990s, organizations slowly proceeded by considering safety measures including cruise and brake controls. After the turn of the century, blind spot detection and electronic stability controls through sensors were made available in self-driven vehicles. One of the biggest achievements in the year 1995 was the VAMP-designed autonomous vehicle that drives, almost, by itself for 2,000 kilometers. Between 1995 and 1998, the National AHS Consortium was held for cars, followed by the PATH organization that conducted the automated bus and truck demos. In the year 2009, the Google self-driving car project began. Eventually, Tesla Multinational Automotive released the update in Autopilot software. Self-driving cars designed by Google, having met with a test drive accident in the year 2016, were considered a major damage to the development of AVs. At the end of 2016, the Bolt and Super Cruise and Cadillac have autonomous controls. At the start of January 2022, Volvo unveiled Ride Pilot, a new Level 3 autonomous driving technology, at the CES Consumer Electronics Expo. Without human input, the system navigates the road using LiDAR, radar, ultrasonic sensors, and a 360-degree camera setup. Figure representation of the AV system. As of 2019, self-driven vehicles possess the following features. Freehand handles the steering, but monitoring the system is also needed. With additional improvement in freehand steering, the Adaptive Cruise Control, ACC, keeps the vehicle at a predetermined displacement from the surrounding objects. When an interruption is encountered, like the motorist crossing the lane, the car insists that the system slows down and changes the lane. One of the main problems with AV mobility is how to combine sensors and estimate circumstances to distinguish between risky scenarios and less dangerous ones. AVS mobility is quite tedious, but continuous accepted releases in this field give better mobility to the vehicles. AI gives a fantastic change in the technological revolution. The Department of Transportation, DOT, and NHTSA deal with safety in addition to automation protocols. Section of this chapter presents a detailed survey of machine learning and deep learning algorithms used in the AV literature, where the important AV pipeline activities are analyzed individually. Section presents a survey of the state-of-the-art datasets used in autonomous vehicles, and section discusses the industry standards, risks, challenges, and opportunities, with section summarizing the analysis. Research trends of AI for AV to provide readers a comprehensive picture of the status of the literature in AI on AV. The current research trends of ML/DL algorithms in the design of autonomous vehicles are presented. The systems rely on several technological advancements in AI technicalities. When looking into the automation ideology in vehicles, it comprises 6 different levels. Starting from level 0, the human driver operates with no self-control in the cars. We could say that there is no self-working at level 0. At the first level, the Advanced Driver Assistance System (ADAS) in vehicles supports the driver with either accelerating or steering controls. In addition to level 1, the ADAS provides brake controls to the system, such as Automated Emergency Braking System (AEBS). However, the driver must pay complete attention to the surroundings. Level 2. At level 3, almost all automation processes are performed by the system, but driverless access is required in certain operations. Real-time high-definition maps must be accessible, complete, and detailed. These maps are necessary, and they are used to decide their path and trajectory. Further development of Level 3 is that the Vehicle's Advanced Driving System (ADS) provides complete automation without a human, even if a person does not respond to a request in some circumstances. A vehicle's 6 degrees of freedom are indicated by the stance, which is monitored by AV pose sensors X, Y, Z, and, here, X, Y, and Z depicts actual positions of the system at level 4. Eventually, at level 5, Virtual chauffeur concept is introduced by ADS along with ACC and does all the driving in all circumstances. Autonomous vehicles can be successfully implemented in a range of use case situations combining the complete working of sensors, actuators, maps, detectors, etc. It is necessary to demonstrate the functionalities in real-life environments like urban and rural developments combining smart vehicles. LiDAR technology ensures the functional and safe operation of an autonomous vehicle. LiDAR is more efficient in creating 3D images of the surroundings that is considered critical in urban settings. 1. A rotating roof-mounted LiDAR sensor creates and maintains a live 3D map of a 60 m range of surroundings and thus generates a specific route for travel to the destination specified by the driver. Radars are mounted to measure the distance between obstructions and are placed at the front and rear. To determine the car's south position in the lane concerning the 3D map, a sensor on the left rear wheel tracks and signals the system's sideway movement. All of the sensors are connected to the AI program, which receives the dataset in accordance. Thirdly, collaborative mapping efforts gather massive amounts of raw data at once utilizing GPS technologies to recover information on traffic signals, landmarks, and construction projects that cause deviations. By acquiring more knowledge on the NVH behavior of the entire vehicle, the vehicle's performance systems can be improved. Utilizing SimCenter NVH systems has additional advantages, such as AI-based strategies for improving the effectiveness of NVH testing, and NVH performance prediction without the need for intricate simulation models. After the development of the 3D models, the developers focused on substances in the surroundings. A revolutionary YOLOv2 vehicle architecture has been developed to address accuracy-based concerns, enhance sluggishness identification, and solve the lagging in classification criteria. An autonomous driving system was overlaid with augmented reality, AR, displayed on the windshield. AR vehicle display systems are necessary for navigation. Situational awareness has been considered as the command line interface that was developed using AR technology. The INRIA dataset was used to identify vehicles and pedestrians as part of the demonstration of an AR HUD-based driving safety instruction based on an article released by SAE International. SVM and HOG algorithms have been used to build the identification method, which detected partial obstacles with 72% and 74% accuracy in frames per second. 2. Since improvement in the above system has been demanded, technologists modeled a better version through the use of stereo cameras and augmented reality. The forward collision alert system detected vehicles and people and showed early warnings while applying an SVM classifier for apprehension that received % for identifying cars and % for identifying pedestrians. 3. Although it was challenging to establish the motion detecting strategy, the model was able to control the car in confusion situations. This method established a rule base to handle illogical situations. The method might complete M of designing a path in S4. The study suggested the use of R-tree data structure and the continuous nearest neighbor search. 5. To simulate 3D rain, stereo pictures are used. The method can be used for already existing photographs, preventing the need to retake. The recurrent rolling convolution, RRC, for object prediction and KITTI dataset were employed in the study S-tests at the Karlsruhe Institute of Technology. The results of testing 450 photographs reveal that the algorithm S measured average precision decreases by %6. The most likely to happen 5G-enabled vehicle autonomy says that through CRAN, autonomous and connected vehicles running on 5G will be able to access cloud-based ML/AI to make self-drive decisions. In high mobility settings, edge computing and 5G can greatly speed up and improve data decryption. In these cases, edge computing-based data analysis and processing are automatically executed in the servers that are nearest to the cars. This might significantly lessen data traffic, remove internet constraints for handling greater speed in data transfer, and lower the expense of transmission. 7. The researchers confirm that high-speed internet access can improve data transaction, and eventually, autonomous driving is highly benefited by the same. The stochastic Markov decision process, MDP, has been used to simulate how an autonomous vehicle interacts with its surroundings and learns to drive like an expert driver. The MDP model considers the road layout to account for a wider range of driving behaviors. The autonomous vehicle's desired expert-like driving behavior is achieved by choosing the best driving strategy for the autonomous car. A deep neural network, DNN, has been used to make an approximation of the expert driver's unknown reward function. The maximum entropy principle, MEP, has been used to train DNN. The simulations show the ideal driving characteristics of an autonomous vehicle. The use of the MEP has been modeled to train a DNN's reward function. Additionally, essential derivations for applying the MEP to know the applications and workings of a reward function have also been offered. Certain functionalities. 8. AV pipeline activities. Each domain was examined by looking at various approaches and techniques and comparing their benefits, drawbacks, results, and significance. To hasten the construction of a Level 4 or 5 AVS, the examination of each domain is summarized as follows. Vehicle detection. This section analyzes deep learning methods, which are used for quicker and more precise vehicle identification and recognition in a variety of unpredictable driving situations. This paper suggested an online network architecture for identifying and tracking vehicles. Using the KITTI dataset 9 and a trajectory approximation of LSTM, the framework changed 3D poses when instances were moved around in a global coordinate system, outperforming long-range LiDAR results. LiDAR obtained false negatives in a 30m range. LiDAR-based false negative scores for 50m and 10m tests have been mentioned as in 1:10. To improve recognition speed, and as a way of resolving it, a novel YOLOv2 vehicle architecture was proposed. 11. One of the main problems with the real-time traffic monitoring approach was the low resolution of the images, which may be attributed to factors like poor weather. Vehicles in low-resolution photographs and videos were examined for this issue in terms of CNN's effectiveness. The architecture utilized by the neural network operated in 2 stages. First, it detected high-level features, and then it detected low-level attributes. It evaluated the model's capability to recognize automobiles at various degrees of input resolution. Results state that CNN is surprisingly positive in the identification even with low resolution. 12. Liu et al. Demonstrated the least complex approach for AVS by combining a lightweight YOLO network. The technique was applied to a dataset that was created by themselves and, within MS, achieved % precision. This could be a turning point for AVS, a quicker and more precise solution for diverse fields of vision and implementation during the day or at night. 13. Rear-end collision avoidance. Collision negatively influences road safety and the assurance for a safe ride. Wide and varied publications emphasize extensively for proposing methods to reduce collisions based on different approaches such as collision avoidance, collision warning, and collision risk assessment, VANIT. These algorithms were implemented in Vehicular Ad Hoc Network. In this paper, 14, the authors proposed a collision avoidance theory model. This model works by giving weights to the inputs. Certain characteristics like driver's age, visual power, mental health, and physical health conditions are provided to the algorithm. The algorithm computes the weights for the characteristics, processes the input, and generates the output. Generally, the output is always a warning. The implementation of the algorithm was done in MATLAB, and the other platform of implementation was VisSim. The above paper was completely based on human factors, whereas the other model called collision warning that was discussed by the authors considers human factors and weather situations and timings. This algorithm highly focuses on the visual power of humans and puts forth a visuality-based warning system. The MATLAB software and Prescan commercial software were used for testing the visuality-based warning system. This system is accepted to provide better performance than the other warning systems. To prevent crashes, a multi-factor-based road accident prevention system, MBRAPS, was suggested. The implementation made use of MATLAB and NetLogo. Based on a previous study, the authors are retrieving new significant elements that might aid collision avoidance algorithms in a more efficient manner in this work. They added these fresh parameters to MBRAPS to improve the V2V collision warning system. The suggested algorithm activates the various functions of the driver assistance system to control the speed and apply the brake after estimating the likelihood of an accident. The alarm is produced as necessary by the driver assistance system. 15. Traffic signal and sign recognition. The literature on traffic sign recognition is very vast, and there are so many unsolved questions yet to be addressed by researchers from all over the world. Traffic sign detection is indispensable in the design of the autonomous vehicle, as the signs communicate commands to the driver in place to take appropriate actions. The results of traffic sign recognition using the GTSRB dataset is shown in figure. A novel structure named Branch Convolutional Neural Network, BCNN, is now changed into Site Visitors Signal Identification. A branch output mechanism was introduced to the architecture and inserted between the pooling and convolutional layers to increase the recognition along with the machine's speed and accuracy. The BCNN-based technique performed exceptionally well in complicated visual settings. 17. The LeNet-5 CNN architecture was used to train the 16 varietal Korean traffic. The practice set consisted of true positives 25,000 and false positives 78,018. Additionally, a convolutional traffic light identification feature for AVS based on quicker RCNN is appropriate for traffic light identification as well as categorization. They applied their method to a sizable dataset called DriverU traffic light and got an average precision of 92%. However, restrictions on false positives will be depreciated by using a strategy or an RNN. 19. Traffic sign recognition based on the HSV color model by the LeNet-5 architecture with Atom Optimizer was proposed and tested with the German technology-based traffic identification and yielded a median accuracy of with ms per frame. 20. Deep TLR traffic light recognition and classification system are a real-time vision-dependent, intricate, and very complex system that did not want positional information or temporal principles. 14. The GTSRB dataset served as the training set for majority of the deep learning techniques. In the LetNet-5-based CNN on a self-created dataset with spatial threshold segmentation using the HSV, the GTSRB dataset scored the best for traffic sign identification, despite a decline in performance in a complicated environment and the detection of separated signs. Despite a drop-off act in a composite setting and the apprehension of divided indications on account of the submitted extent, the GTSRB dataset outperformed the LetNet 5-based CNN on a designed dataset accompanying geographical opening separation adopting the HSV. Despite relying on pre-labeled data, the YOLO method-based technique for traffic light detection with recognition of interior signs obtained the highest accuracy in the shortest amount of time from the above discussed, 21. Figure traffic signs from the GTSRB dataset, 16. Lane detection and tracking. Lane detection and tracking have been considered as essential modules in a complete autonomous vehicle system. In various literatures, it has been considered as an important field of research in autonomous vehicles, and many algorithms have been proposed to solve the encountered problems of lane detection and tracking. It is an important module that solves the perception problems of autonomous vehicles. In comparison with straight lane detection, some literatures introduce curved road lane detection tracking as challenging and important to avoid accidents. Figure shows straight lane line and curved lane line respectively. This paper categorized the lane detection methods into three as feature-based, model-based, and methods based on other trending technologies and discussed a novel curved road detection algorithm, where the road images were initially divided into ROI and the background. The ROI has been further divided into linear and curved portions. The proposed approach evolved as a series of mathematical equations and Hopf transformation. It has been concluded that the proposed algorithm effectively identifies lane boundaries and to be effective enough to assist drivers, improving safety standards. 22. Figure straight lane line. Figure curved lane line. This paper presented a lane detection and tracking approach based on Gaussian sum-particle filter. The proposed feature extraction approach in this paper was based on the linear propagation of boundary and lane points while zooming in. Three types of algorithms used for tracking, namely, SIR particle filter, Gaussian particle filter, and the used GSPF, are compared, and it has been concluded that GSPF outperforms the other two widely used tracking algorithms. 23. This paper presented a survey of trends and methods in road and lane detection, highlighting the research gaps. 7 different modalities, namely monocular vision, LiDAR, stereo imaging, radar, vehicle dynamics, GPS, and GIS, have been utilized for perception of roads and lanes. The survey highlighted the gap in the literature of perception problems of multiple lane roads and nonlinear lanes. Detection of lane split and merges has been proposed as an unnoticed perception problem to be solved in the near future for the development of fully autonomous vehicles. Lack of established benchmarks has also been discussed as an important issue in order to compare the currently efficient methods in different scenarios. 24. This paper compared the computer vision-based lane detection techniques with sensor-based algorithms. The traditional modules in conventional computer vision-based lane detection algorithms as highlighted in the survey are image pre-processing, feature extraction, fitting the lane, and the tracking module. Popular edge detection operators such as Canny, Sobel, Pruitt, line detection operators, and thresholding techniques have been highlighted as the popularly used feature extraction techniques based on the assumptions in the structure, texture, and color of the road. The potential of deep learning for automatic feature extraction and to learn the environment with most variance conditions has been highlighted. The survey also criticized the lack of benchmarked datasets and standard evaluation metrics to test the efficiency of the algorithms. 25. In this paper, 26, the authors presented a detailed survey of deep learning methods used in lane detection. The survey categorized the state-of-the-art methods into two based on the number of modules as two-step and single-step methods based on feature extraction and post-processing. Classification, object detection, and segmentation-based architectures have been detailed as three types of model architectures used for lane detection. The paper also discussed the evaluation metrics of different algorithms based on the two-simple dataset, which has been regarded as the largest dataset for lane detection. Based on the analysis, the CNN-LSTM, SegNet+, architecture has been reported to have the highest accuracy of %. The computational complexity of deep learning models like CNN and RNN has been emphasized as a disadvantage for implementation on low-memory devices. In this paper, 27, the authors applied a new CNN learning algorithm for lane detection, namely, Extreme Learning Machine (ELM), to reduce the training time, also by using a relatively smaller dataset for training. The training time of the ELCNN has been reported to be 800 times faster, and the experimental results established that incorporating ELM into CNN also increases the performance of the model based on accuracy. This paper emphasized an edge cloud computing-based CNN architecture for lane detection, where the concepts of edge computing and cloud computing have been introduced to increase the data processing efficiency for real-time lane detection. Their approach achieved fair accuracy than other state-of-the-art algorithms in challenging scenarios of insufficient light, shadow occlusion, missing lane line, and curved lane line. The accuracy achieved on normal road conditions was, and all of the evaluation metrics have been derived based on the two-simple dataset, 28. In this paper, 29, the author proposed a multiple frame-based deep learning lane detection architecture using CNN and RNN to avoid the ambiguities that arise due to detections based on a single frame in the presence of shadow, occlusion of vehicles, etc. The continuous scene-based architecture has CNN layers, where the multiple frame input-outputs constitute time series data that are fed into the recurrent neural network. The CNN architecture acts as the encoder-decoder circuitry for reducing the size of the input, and the LSTM architecture determines the next scene, thus detecting the lane. The work laid a strong foundation for using CNN-RNN architectures for detecting lanes in challenging scenarios. It established the idea that the situations that cannot be analyzed using a single image input can be improved by using a multiple frame input architecture. In this paper, 30, the authors introduced YOLO-based obstacle and lane detection algorithms based on video inputs and two simple datasets. The inverse perspective transform has been used for constructing the bird's-eye view of the lane. The deep learning models are criticized for their poor performance, and their YOLO-based architecture achieved an accuracy of % for lane detection within a time span of s. This increased speed of processing has been claimed advantageous for implementation in real-time autonomous vehicle scenarios. Pedestrian detection. One of the main vision-based issues for AVS is accurately recognizing and localizing pedestrians on roads in a variety of settings. The study of vehicle autonomy aims at increasing the accuracy in identifying and localizing the pedestrians to prevent fatalities. Numerous studies have been successful in lowering accident rates and developing a more accurate and long-lasting approach to autonomous driving technologies. The approaches used for pedestrian detection can be broadly categorized into two as those that use man-in-the-loop feature extraction and deep learning-based methods. For pedestrian detection, a most sought deep learning model is the convolutional neural network, which has been used in many studies to detect pedestrians. In that way, a deep grid named Large Field of View, LFOV, was imported to uniformly skim perplexing representations of walkers. The submitted structure was created to analyze and create categorization judgments across a broad extent of neighborhoods concurrently and efficiently. The LFOV network can implicitly reuse calculations since it analyzes enormous regions at higher speed that are substantially faster than those of standard deep networks. This pedestrian detection system demonstrated a convincing performance for practical application, taking 280 milliseconds per image on GPU and having an average miss rate of %31. For passers-by discovery, a new CNN structural version was proposed, 32. To annotate the positions of pedestrians in the model, they used synthetic photographs and transfer learning, together with a bounding box suggestion for an uncovered region. When crowded scenarios were taken into account, it got a 26% lost count in the CUHK08 dataset and a 14% missing proportion in the Caltech Walker dataset. The major benefit was that it did not need a region proposal method and did not require explicit detection during training. In this paper, 33, the authors presented a detailed survey of the state-of-the-art pedestrian detection algorithms in the domain of automobiles and safety. The position of humans on the lane, pose, color, environment, weather, texture, etc., increase the complexity of the pedestrian detection problem, making the classical template matching approach to be inefficient for real-time detections. The feature-based detection approach requires man-in-the-loop feature extraction methods, whereas deep learning models self-learn features during training. This has been highlighted as an advantage of deep learning-based detection methods where the models can achieve fair accuracy with a huge training set. However, both the approaches have been considered to be implemented on par with each other. CNN has been regarded as the most widely used algorithm for pedestrian detection. Bounding box, missing rate, TP, TN, FP, FN, false positives per window, AMR, and IOU are regarded as the most commonly used evaluation metrics. It has been concluded that accuracy and cost are still a trade-off to be balanced in pedestrian detection, as the robust solution to this complex problem is yet to be proposed more efficiently. In this paper, 34, the authors exemplified the similarities between pedestrian detection pipeline and object detection pipeline and conducted experiments to optimize a CNN-based detection pipeline for pedestrian detection. Sliding window, selective search, and LDCF algorithms have been tested for best efficiency in the selection of candidate regions. Selective search has been concluded not suitable, the sliding window approach achieves better recall, and the LDCF algorithm has been concluded as the best region proposal algorithm. Their approach has been evaluated based on the Caltech pedestrian dataset using error metrics such as MR and FPPI. The entire experiment has been tested on the NVIDIA Jetson TK1, the most widely used hardware in smart cars. In this paper, 35, the authors proposed a hybrid approach by combining HOV, LOVE, and CNN classifier, namely, the multilayer channel feature framework. It has been discussed that by eliminating the overlapping windows, the cost of CNN has been reduced. The proposed approach has been evaluated in the Caltech, KITTI, INRIA, TUD Brussels, and ETH datasets. The performance of MCF has been considered fair in comparison with the state-of-the-art methods. In this paper, 36, the authors proposed a feature-sharing-based deep neural network architecture for pedestrian detection, thereby reducing the computational cost of feature extraction during the model training phase. Feature sharing has been emphasized among the different CONVNet-based detectors that differ in their model window sizes. INRIA and Caltech have been used for the evaluation of their approach, and it has been reported using 4 CONVNet detector units. The time for detection decreased almost by 50%. In this paper, 37, the authors criticized the slow detection speed of conventional deep learning algorithms and used YOLO architecture for pedestrian detection. The experiments have been trained using the INRIA dataset and a few selected images from Pascal VOC. YOLO v2 has been concluded to have a higher detection speed than the presented approach in the paper. In this paper, 38, the authors proposed a two-modular pedestrian detection architecture based on convolutional neural networks. In the region generation module, contrasting to image pyramids, feature pyramids are used to capture features of different resolutions. The modified ResNet 50 architecture has been used as the background network of both modules. The deep supervision-based region prediction module thus achieved a precision score of % and an MR of %. It has been concluded that a fair trade-off balance has been achieved between real-time predictions and accuracy. In this paper, 39, the authors proposes a convolutional neural network architecture for real-time pedestrian detection tasks. The approach signified a lightweight architecture for real-time detection and warning to avoid accidents. A regression-based problem-solving approach has been implemented in contrast to the conventional classification modules to increase the inference speed. Pruning and quantization techniques have been highlighted as the model compression techniques employed. The observed inference speed was 35 frames per second with a map of 87% in the specifically designed hardware for autonomous vehicles. Hazy weather pedestrian detection has been considered even more challenging than the clear day pedestrian detection. In this paper, 40, the authors proposed a hazy weather pedestrian detection framework based on a modified YOLO architecture, reducing cost, thereby improving accuracy. The contributions made in the research work also include a hazy weather pedestrian detection dataset. They present 3 YOLO-based detection models, namely, Simple YOLO, VGG Prioriboxes YOLO, and MN Prioriboxes YOLO. The MN Prioriboxes YOLO that uses depth-wise convolutions based on the MobileNet v2 architecture has the least number of parameters among all of the other methods. It has been concluded that the strategies employed reduced the number of parameters, thereby decreasing the running time of the algorithm. In this paper, 41, the authors presented an approach to pedestrian detection in nighttime scenarios using multispectral images based on CNN. The authors studied different image fusion and CNN fusion methods. The pixel-level image fusion technique has been considered superior to CNN fusion methods. All of the experimental conclusions presented in the research work were based on the KAIST multispectral database. In this paper, 42, the authors considered the multispectral approach to pedestrian detection as a solution to solve challenges encountered in cases of detection in poor illumination, occlusion, etc. The RFCN-based detector has been used, and information on both the color and thermal images is fused using a network in the network model. Their approach evaluated based on the KAIST dataset revealed that the proposed approach has better performance than the other state-of-the-art methods implemented for multispectral images. Datasets in the literature of autonomous vehicles. Datasets contain advanced and to a certain extent upgraded information in many scholarly studies by benefiting to solve legitimate experience models of issues. They enable quantitative analysis of methods, revealing important information about their strengths and weaknesses. The performance of algorithms must be ensured on real-world datasets. Algorithms used, for instance, must deal with complicated objects and settings while contending with difficult environmental factors like direct illumination, shadows, and rain. This section surveys the current datasets used in the literature of autonomous vehicles. Stereo and 3D reconstruction. To evaluate the effectiveness of stereo matching algorithms, the Middlebury Stereo was developed in 2002 that created the Middlebury Multiview Stereo, MVS. Being only 2 scenes in size, the benchmark was crucial in the development of MVS methods. In comparison, 124 diverse scenarios were captured in a controlled laboratory environment. Light scans from each camera position are combined to create reference data, and the resulting scans are extremely dense, with an average of million points per scan. The whole 360-degree model for 44 sceneries were created by rotating and scanning in contrast to the datasets so far. High-resolution data were captured. DSLR images and synced stereo videos in various interior and outdoor settings were also included. With the use of a reliable procedure, all images can be registered using a high-precision laser scanner. The evaluation of a thorough 3D reconstruction is made possible by high-resolution photographs. 43. Optical flow. The mobility concept in AI has a huge capability and upgrades the working efficiency by collecting enormous amount of data, and norms will direct the system to the output platform. Thereby, it meets the goal of vehicle autonomy. A toothbrush is used to track concealed fluorescent presence on the objects in all non-fixed sequences to decide the base reality progress. The dataset is made up of 8 distinct sequences with a frame count of 8 each. For each sequence, a pair receives the ground truth flow. 44. Contrary to other datasets, the Middlebury dataset offers extremely accurate and deep ground truth, which enables the evaluation of subpixel precision. Accurate reference data are generated by monitoring pixels over extensively sampled spacetime volumes using high-speed video cameras. With this technique, optical flow ground truth may be automatically acquired in difficult everyday settings, and realistic elements like motion blur can be added to compare approaches under various circumstances. Recognition and segmentation of objects. The Microsoft COCO dataset was introduced in 2014 for object detection. They offer visual representations with intricate scenarios with typical items established in their normal surroundings. The count of situations by means of division for Microsoft COCO is indeed above in consideration of the Pascal VOC target separation standard. The dataset contains 328K photographs, million commented details, and 91 object classes. In a significant crowd, all objects have per-instance segmentations tagged on them. The intersection over union measure is employed for evaluation, much like Pascal VOC. 45. Tracking datasets. Multi-object tracking benchmarks consists of 14 difficult video sequences shot in unrestricted contexts with both stationary and moving cameras. The trio groups were annotated, moving or stationary walkers, humans who are not standing up straight, and others. They assess the approaches using 2 well-known tracking standards, MOTA multiple object tracking accuracy, and the other one is MOTP multiple object tracking precision. 46. Datasets for aerial images, data from air sensors for the detection of urban objects as well as the reconstruction and segmentation of 3D buildings were indicated by the ISPRS benchmark. It is made up of the Vehingen and Downtown Toronto databases. The scene in a road setup is the object classes taken into account in the object detection process. 3 locations with different object classes and sizable road detection test methods are available in the Vehingen dataset. There are 2 smaller sections for building reconstruction and object extraction, similar to Vehingen. Sensor synchronization datasets. A camera S-Sync connects different levels and angles of photographs. The exposure trigger time is represented by the timestamp of the image, and the full rotation of the current LiDAR frame is represented by the timestamp of the LiDAR scan. This method typically produces good data alignment since the camera S-Sync is instantaneous. 47. Current industry standards in AV. Innovative technologies like AVs come with risks and consequences that could reduce society's acceptance. These risks include those related to the environment, market, society, organizations, politics, economy, technology, and turbulence. The examination of 86 documents produced by 29 leading AV technology firms summarizes the industry standards. The main topic of this essay is a technological risk that is defined as potential adverse social, economic, and physical effects linked to individuals' worries about utilizing cutting-edge technologies. The consequence is that since no single framework can adequately account for the wide range of potential machine decisional applications, we should not try to create a generic one-size-fits-all model of artificial intelligence application. AVs are related to 5 different categories of technological risk: security, privacy, cybersecurity, liability, and industry impact. Governments must implement new policies and laws to resolve the risks connected with AVs to guarantee the society with benefits as much as possible from the developing AV sector. According to estimates, human error is to blame for at least 90% of automobile collisions. By surpassing drivers, humans, in perception, decision-making, and execution, AV adoption potentially reduces or eliminates the main cause of auto accidents. According to authors Collingwood and Littman, very less drivers use seatbelts and pedestrians may become less cautious as a result of feeling safer. This means that a nonlinear relational model of classification notions must be constructed and that the technology must be accepted at face value to appropriately frame each unique choice situation. Additionally, the absence of human mistakes does not imply the absence of mechanical error. The possibility of scientific weaknesses risking vehicle security hikes in addition to the ramification of telecommunications. The catastrophic Tesla automatic steering system accident in 2016 emphasizes the obstructions of component skill in order to avoid accidents and discovered the vagueness of the developed arrangement understanding. Concerns are raised about how crash algorithms should be used to program AVs to react in the event of inevitable accidents. Rules to control AVs' responses to moral standards are necessary because the harm produced by AVs in accidents cannot be subjectively assessed due to the absence of responsibility. The overall tone of the AV reports examined for this study is predominantly favorable. However, this finding must be taken in the context of the fact that these reports are prepared for a specific group of stakeholders, including investors, consumers, and regulatory bodies. The AV industry papers make numerous references to ethical dilemmas, even though deficient in the definiteness and insight of the descriptions in the experimental essay. It manifests that prevalent reliability, sustainability, comfort, human listening, control, and scrutinizing, as well as the science-policy relationship, are the ethical issues that were handled by most organizations, with safety and cybersecurity coming in second. Challenges and opportunities in AV. Without a doubt, the driverless car has many benefits, such as providing a means of transportation for people who cannot drive and reducing the driver's stress on roads. However, in addition to these positive outcomes, numerous obstacles were encountered and they have to address to implement a successful AV model. The subsequent are few of the predominant difficulties. Alongside driverless Jeeps, numerous automakers had to invest a significant sum of money in constructing these autonomous vehicles. One can use Google as an example, which pays about $80,000 for one of its AV models, making it completely out of reach for the average person or business. This price is expected to decrease by half in the future, which is still more affordable, according to projections. According to a recent J.D. Power survey, 37% of consumers say they will select an autonomous vehicle as their next vehicle in the future. Security concerns. The largest problem with electronic systems is usually security and privacy. The AI system that autonomous vehicles are based on needs internet connection to manage and transmit information, making it a vulnerable medium that hackers can exploit. The second main worry is the possibility of terrorist action, where the autonomous car platform could provide a convenient location for them to execute their self-murder duty. Moreover, the Jeeps depend on GPS schemes. Anybody can operate them for malicious purposes by gaining access to them. Standards and regulations. There are some rules and regulations that must be established before autonomous vehicles can be used. Not only the owner of these vehicles but also the automakers using this technology must formally adopt and strictly adhere to these criteria. The United States has proposed the following laws and guidelines that include Nevada, NRS 482, A and NAC 482, and California, CalVE. Code Division. Conclusion. This chapter highlighted the research flows and issues related to artificial intelligence in autonomous cars, elaborating on the history of autonomous vehicles. SVM is identified as the ML algorithm that has been given significant importance for the development of classification models in AV literature. Other than SVM, mostly deep learning algorithms such as CNN, RCNN, and YOLO architectures are utilized for all of the object recognition and classification jobs. The performance of the model highly depends upon the quality of data. Deep learning algorithms require huge datasets to achieve fair accuracy. KITTI, KAIST, COCO, Pascal VOC, GTSRB, INRIA, and TuSimple are some of the benchmarked datasets observed to be widely used in the survey. In the AV pipeline activities, machine learning-based algorithms demand the man-in-the-loop feature extraction method, hence, deep learning has been suggested as the better alternative. However, due to the computational complexity of the deep learning models, they are not suitable for real-time implementation. The literature on AI and AV profoundly suggests the design of both less costly and more accurate design models solving the problems of AV pipeline activities. For object detection and recognition activities, YOLO replaced the traditional convolutional architectures. For edge-based implementations, in a few research papers, edge-compatible lightweight convolutional architectures are proposed using techniques such as depth-wise separable convolutions. Lack of proper and benchmarked datasets for the comparison of the state-of-the-art algorithms has been reported in a few literatures. Several studies also suggested that the performance of the algorithms may not be the same in all of the datasets. Hence, without proper comparison based on datasets, the efficiency of the algorithms cannot be concluded. The modules described in the AI pipeline, for example, pedestrian detection, has been regarded not only in the literature of AV but also in other domains of research where there are necessities to identify humans. The literature of AI in autonomous vehicle can be concluded as the booming field of research with more focus laid on the development of self-driving cars, ADAS, etc. With the advancements of cloud computing, edge computing, and the swiftly refined designs of edge-compatible GPU, the research in AV promises advanced outcomes in the future. 2 Age of Computational AI for Autonomous Vehicles Akash Mohanty 1, U. Rahamathanasa 2, K. Sudhakar 3 and R. Sathiraj 4 *1 School of Mechanical Engineering, Vellore Institute of Technology, Vellore, Tamil Nadu, India 2 School of Information Technology and Engineering and Technology, Vellore Institute of Technology, Vellore, India 3 Department of Computer Science and Engineering, Madanapal Institute of Technology, Madanapal, Andhra Pradesh, India 4 Department of CSE, Jidam School of Technology, Jidam University, Bengaluru, Karnataka, India. Autonomous vehicles have made a great impact on research and industrial growth over the past era. The automobile industry is now being revolutionized by self-driving, or driverless, technology owing to enhanced and advanced autonomous vehicles that make use of cutting-edge computational methods from the fields of machine intelligence and artificial intelligence, AI. Autonomous vehicles are now able to assess their surroundings with high accuracy, make sensible choices in real-time environments, and function legitimately without human intervention and technological advancements in the arena of computationally powerful AI algorithms. The development of autonomous vehicles relies heavily on cutting-edge computational technologies. The chapter aims to review the contemporary methods of computational models over time and presents the computational models in the arena of machine learning, its subset deep learning and artificial intelligence. The chapter initially discusses the role of AI, followed by its autonomy levels. The learning algorithms that perform continual learning are addressed along with advances in intelligent vehicles. We disparagingly evaluate the key issues with computational approaches for driverless complex applications. Integration of computational technologies is presented in brief, addressing how technologies can empower autonomous vehicles. Classification of technological advancements with future directions was given and concluded. Autonomous vehicles, computational methods, artificial intelligence, machine learning, deep learning, continual learning, classification. Intelligent vehicles introduction. Autonomous vehicles are vehicles that can operate independently of a human driver, a scientific development that aims to revolutionize transportation and is currently one of the biggest trends. Although the development of autonomous vehicles has gained popularity over the past 20 years, it is true that it first began in the 1990s. Francis Hodina, an electrical engineer from New York, was the first to put the idea of an autonomous vehicle into practice in 1925. However, his vehicle required remote control. A car crashed with the prototype while it was on display to the public in Manhattan, delaying its path for nearly 19 kilometers between Broadway and Fifth Avenue. Chandler, Hodina's car, was nevertheless created between 1926 and 1930. A Mercedes-Benz van was later transformed into an autonomous vehicle in the 1980s by the German Ernst Dickmanns, who is regarded as the inventor of the modern autonomous vehicle. This vehicle was driven by an integrated computer. The vehicle was able to travel 63 km/h through streets with no traffic in 1987. Similar maneuvers were made in 1994 with a car that covered more than 1,000 kilometers through congested Paris. A Mercedes-Benz made an autonomous trip from Munich to Copenhagen in 1995. These initiatives were funded by the European Commission as part of Project Eureka, which gave Dickmanns over €800 million to conduct this kind of vehicle research. Driverless cars are indeed a major topic in the realm of vehicular technology, which now has rapidly grown in prominence. 1. Over the past few decades, numerous businesses and scholars have become interested in the burgeoning field of autonomous driving, which includes self-driving automobiles, drones, trains, and agricultural equipment in addition to military uses. 2. The first radio-controlled Chandler, American Wonder, which introduced the idea of autonomous driving, was displayed in New York City in the 1920s. 3. After several years, Carnegie Mellon University built the first self-driving car, which was given in 1986. It is merely a van that can drive itself. In 2005, a different team from Carnegie Mellon University developed a self-driving car that was successful over an 8-mile range and won the DARPA Grand Challenge. 3. In 2010, Google researchers created an autonomous vehicle that has already driven over 140,000 miles between San Francisco and Los Angeles. Self-driving hardware was implemented into the products of many automakers in 2016. 3. Comprising Mercedes-Benz, BMW, Tesla and Uber is used by various transit companies. Several categories of automated vehicles, such as drones or trains, may evolve more rapidly while their habitats have been less influenced by human activities than automated vehicles. The central concept behind self-governing vehicles is to employ artificial intelligence, AI, to intelligently guide the vehicles depending on their surroundings. 4. These disciplines include A. Machine learning supervised and unsupervised approaches for decision-making, B. To analyze the information from video, deep learning and computer vision technologies were used, and C. To ensure vehicle safety and control, sensor-based processing techniques were applied. 4. 5. The progress of autonomous vehicles, 1. Also strongly depends on improvements in distributed hardware devices, namely, big data technologies and network connectivity, and utilizes graphical processing units, GPUs, for quick processing. 6. 7. Autonomous vehicles. Automated vehicle users are enthusiastic about its advent to the public sector. A self-driving vehicle is one that can run unsupervised and without human interference. Modern autonomous vehicles, according to Campbell et al., 9, can assess their immediate surroundings, classify various items they come across, and interpret sensory data to choose the best routes to take while adhering to traffic laws. Remarkable encroachments been formed in generous irrelevant reaction to unforeseen circumstances wherever there may be a payback in the drive systems or where an outward medium might not perform as anticipated by underlying prototypes. To successfully execute self-governing navigation in those kinds of situations, it is crucial to integrate a variety of technologies from various fields, notably electronics engineering, mechanical engineering, computer science, control engineering, and electrical engineering, among many others. 8. The first radio-controlled car, known as the Lincoln Wonder, marks the beginning of the autonomous vehicle era in 1926. The emphasis has been mostly upon vision-guided structures consuming GPS, LiDAR, computer vision, and radar from the launch of the vision-guided vehicle Mercedes-Benz, a robotic van in the year 1980, and there have been considerable developments in technology for autonomous vehicles since then. As a way, steer assist, adaptive cruise control, and lane parking became autonomous technologies seen in modern cars. We will eventually live in a world with fully autonomous vehicles, as per official projections given by auto manufacturers. Traffic calamities are some of the most prevalent reasons of death globally. The world may avert 5 million civilian mortalities and 50 million major harms by 2020 by putting newer creative ideas into practice and improving road safety at all scales from the small to the global. It is critical, in the opinion of the Commission for Global Road Safety, to put an end to this horrifying and unnecessary rise in traffic accidents and begin year-over-year declines. 9. According to a paper, over 50% of the 3,000 people who pass away each day as a consequence of traffic disasters are not passengers in a car. Deshpande et al. Have also stated that if urgent action is not taken, the number of transportation-related injuries is expected to increase to million annually and rank as the 5th greatest cause of mortality worldwide. The amount of traffic collisions will consequently drastically decline as a result of an automated system's greater durability and speedier response time than humans. Autonomous vehicles would also reduce safety gaps and improve traffic flow management, which would increase roadway volume and lessen traffic congestion. Figure presents a summary of fatalities due to traffic accidents. With the introduction of autonomous vehicles, parking shortages will be a thing of the past because vehicles may pick up passengers, drop them off, park in any available spot, and then pick them up again. There would be less parking available as a result. Physical road signs will become less important as autonomous vehicles obtain all the information they require via a network. Figure summary of fatalities due to traffic accidents. There would be less demand for traffic officers. Autonomous vehicles can therefore cut back on government spending on things like traffic enforcement. Along with a decline in automobile theft, there will also be a reduction in the demand for auto insurance. The elimination of unnecessary passengers altogether will allow for the establishment of efficient systems for the transportation of goods and shared vehicles. Not everyone is appropriate. Therefore, autonomous vehicles relieve the need to drive and navigate. Additionally, commuting times will be shortened because autonomous vehicles can move more quickly with little danger of mistake. The ride will be more comfortable for the car's passengers than it would be in a non-autonomous vehicle. While autonomous vehicles have many advantages, there are also some drawbacks. Although the idea has been disproven, it is still believed that the introduction of autonomous vehicles would result in a decline in occupations involving driving. Another significant difficulty is when drivers lose control of their vehicles because of inexperience, for example. Many individuals enjoy driving, so giving up control of their vehicles would be tough for them. Additionally challenging is the interaction of human-driven and autonomous cars within the same path. Another concern with self-driving cars is who should be held accountable for damage, the automaker, the car's users or proprietor, or the government. Determining a legal mechanism and government regulations for automated automobiles is thus a crucial delinquent. Another significant issue is software reliability. Additionally, there is a chance that the computer or communication system in a car could be hacked. There is a chance that terrorist and criminal activity may increase. For instance, terrorist groups and criminals might pack cars with explosives. They might also be utilized in numerous other crimes and as getaway cars. Autonomous vehicles thus have benefits and drawbacks. This article explores the history of autonomous vehicles in a sequential fashion, starting with historical precedents and moving on to modern developments and projections for the future. The development of autonomous vehicle technology has advanced significantly during the last couple of decades. The vehicle's adaptive, safe, and energy-saving capabilities are significantly enhanced, which establishes it as a distinct area of study for automotive engineering, a trend for the automotive industry, and a force for economic progress. 10. The integration of so many advanced and cutting-edge technologies into autonomous driving presents both obstacles and opportunities in plenty. Critical questions include what the autonomous vehicle's purpose is, what the main technical obstacles are, and how to overcome them so that the objective may be achieved. The computer science is acknowledged as the greatest method for keeping track of research activities and trends. 11. And may be clustered to learn about the hottest subjects in a certain field. 12. It may offer useful details regarding the state of autonomous driving research. This study analyzes the research hotspots that have changed over the last 20 years, pointing out the path for additional research and tracing the evolution of autonomous driving technology. It also discusses recent accomplishments based on bibliometric analysis and literature evaluation. AI in autonomous vehicles. John McCarthy, a computer scientist, coined the word artificial intelligence in the year 1955. Artificial intelligence is the capability of a computer program or machine to reason, learn, and make decisions. In most cases, the phrase describes a machine that mimics human intelligence. Through AI, we can instruct computers and other gadgets to carry out tasks that a human being would do. Such algorithms and devices were pumped enormous volumes of data, which are then evaluated and processed in order to think logically and perform human actions. The primary components of driverless technology were given in figure. AI is being used in automated driving and diagnostic imaging tools with the goal of preserving life, and automating repetitious human labor is simply the idea of an AI iceberg. Functioning of AI in autonomous vehicles. Although AI has recently gained popularity, how will it work in driverless vehicles? Let us think about how a person may drive a car when using his or her sight and hearing to maintain an eye on both the road and other cars. We swiftly decide whether it should stop at a red light or wait for someone to cross the road by using our memory. Decades of driving practice teach us to always look for the little things like a greater speed bump or a more direct route to work. While we are developing autonomous vehicles, we want them to operate similarly to human drivers. Because of this, it is essential to enable these robots access to the sensorial, intellectual, and executive processes that individuals hold when driving a car. The automobile sector has undergone steady change during the last few years in order to achieve this. According to Gartner, multiple V2X, vehicle-to-everything, techniques will connect 250 million vehicles to each other and the associated functions by 2020. Since this quantity of information entered into telematics systems or in-vehicle infotainment, IVI, units increases, vehicles would be able to not only capture and broadcast underlying system status and location information but also alter in their environment in real-time basis. By the addition of sensors, cameras, and communication systems, autonomous cars will be capable to produce massive volumes of facts that, combined via AI, will allow them to see, hear, think, and act in the same ways as human drivers. Figure primary components in driverless technology. Autonomy with no human input. An autonomous vehicle is one that can perceive its environment and operate on its own. A human rider is not required to control the vehicle at any time. Figure portrays a compacted architecture block diagram for autonomous vehicles. Autonomy phases. The term autonomous have multiple definitions, and this vagueness led specialists in the field of autonomous cars to categorize autonomy into different levels, with the following stages denoting the degree of an automated system control and the involvement of drivers in a vehicle. 13. Autonomous levels are summarized in Figure. Level 0. Only optional and necessary hazardous alarms are offered as autonomous and zero-control driving capabilities at this level. Level 1. Drivers still have complete control of the vehicle, but automated controlling systems share that power with them. These cars frequently come equipped with cutting-edge driving aids. Level 2. The automated control system provides the opportunity to take complete control of the car, but the driver is still entirely in charge of operating it. Level 3. The autonomous car can drive completely independently of the passengers, but drivers must take over if the alarm systems call for any physical intervention. Level 4. With no driver's engagement or observation, the automated mechanism takes complete governance of the vehicle, except in unforeseen events where the driver regains control. Level 5. No consideration is given to human interference in this final level. Figure schematic block diagram for autonomous vehicles. Artificial intelligence, which also has fundamentally changed the automotive sector, has hastened the advancement of Level 4 and Level 5 autonomous vehicles. An autonomous vehicle, AV, is a means of transportation that is proficient in handling a range of conditions and drive itself throughout public highways with minimal to no direct human interaction. 14. Intelligent and connected vehicles, ICVs, are a broader and looser concept, and their evolution can be broken down into 4 stages: high/fully automated driving, connected assistance, cooperative automation, and advanced driver assistance systems, ADAS. 15. According to this standard, ICV-SAV stage is its conclusion. Figure autonomous levels. Figure fundamental navigation functions. Figure represents the components required for navigation functionality. The accurate position estimations, the accuracy of the digital plots, then the map matching techniques all play a part in determining the position of a means of transportation for autonomous navigation. Mapping, establishing the spatiotemporal link between the vehicle and its surroundings, is necessary for vehicle guiding. The same can be viewed by means of modeling and comprehending the realm from the perspective of the chauffeur or computer control. Motion. This function can be described as a set of activities that allows the platform to move safely and effectively. These activities include path arrangement to get to the target, collision avoidance, and vehicle control. High levels of interaction exist between the localization, mapping, and actuation tasks. At the vehicle levels, they adhere to a complicated reliant system that is developing in a wildly unpredictable environment. Learning methodologies for incessant learning in real-life autonomy systems. Supervised learning. It is the technique of learning using training information that has been labeled and has comprehensive information of the system's input and output. 16. It is possible to map facts to labels throughout the whole series using supervised incessant learning, which permits learning from sequential streaming data. The complexity of the learning method was decreased by the usage of continuous learning in supervised learning. Unsupervised learning algorithms that do not need labels include those used in unsupervised learning. The most typical application is the training of generative models that replicate the distribution of input data. When the distributional shift happens in the continuous learning scenario, the generative model is modified, causing in the final yield being engendered from the complete input dissemination. The generative replay continuous learning approach has been seen to make the most frequent use of these models. In autonomous systems, Unsupervised continuous learning may be helpful for building progressively more potent illustrations over interval, which can subsequently be fine-tuned via an outward feedback indication from the environments. Unsupervised learning's major objective is to create adequate self-supervised learning signals that can serve as a suitable substitute in order to build adaptable and robust representations. Reinforcement learning: this trains an agent to carry out a series of actions in a particular environment by using a prize function as a tag. It is possible to think of reinforcement learning in complicated environments as a continuous learning situation because they do not afford users admittance to all data at formerly. Reinforcement learning utilizes numerous crucial continuous learning model elements, including the capacity to learn several agents concurrently and the usage of a replay memory, in order to assume data distribution. Additionally, the TRPO algorithm, a well-liked stable reinforcement learning technique, enhances learning in a manner comparable to the continuous learning strategy because of the Fisher matrix used in it. The strong restrictions on reinforcement learning algorithms are the problems of continuous learning. Therefore, enhancing continuous learning will also enhance the effectiveness of reinforcement learning. Unpretentious electromechanical systems gave way towards sophisticated computer-controlled interacted electromechanical systems as ground transportation systems developed. Initially intended for recreation, automobiles are now a crucial component of our daily life. Highly practical modes of transportation. Road infrastructure has been created as a result. The vehicle costs have decreased throughout the years and as a result of mass production and the general public's ability to afford them. However, these modifications have brought up a variety of issues, including fatal or serious injuries, traffic accidents, gridlock, pollution, and aggressive drivers. Advancements in intelligent vehicles: the way that society views transportation networks has altered during the last few years. Automobiles were formerly seen as a source of social status and convenience that gave industry a great deal of flexibility, despite the high accident rate, environmental constraints, high fuel costs, etc. Today's modern transport structures are a basis of significant apprehension. To solve the aforementioned concerns, governments, businesses, and society at large are shifting to what are known as sustainable forms of transportation. Automobile manufacturers are forced by societal expectations for safety, pollution reduction, and networked mobility to continuously adapt their product lines and explore new ways to innovate their offers. Information and Communications Technology, ICT, advancements created prospects for the addition of innovative features to existing vehicles. These vehicles already include a variety of proprioceptive sensors and are gradually adding exteroceptive sensors, which are cameras, radars, and other devices. Additionally, several propulsion methods are employed, and the majority of automobiles utilize their identifiable internal computer networks where diverse nodes handle dissimilar functions. Vehicles can also link to one another and the infrastructure that provides them with constant communication by forming networks. As a result, the car is gradually evolving from a single, mostly mechanical entity into a network of cutting-edge intelligent platforms. 17. Genetic algorithm-based approach for traffic congestion reduction and avoidance with smart transportation focusing on intelligent vehicles is presented. 18. Region identification, extraction of features, and classifications are the three broad classifications of object recognition. 19. The process of employing sensors to find pedestrians in or near an AVS route is known as pedestrian detection. segmentation, extraction of features, segment classification, and track classification are its four constituent parts. 20. A related study looked at how people assign blame for a good or bad event underneath the expectancy violations theory to humans or artificial intelligence agents. 21. The various advanced predictive models were presented. 22. This can be applied for smart traffic management and sustainable environment. An agent-based system for traffic light monitoring and controlling is illustrated. 23. Modern AI algorithms are used by autonomous cars to localize themselves in both known and unknown settings. 24. Regarding short-term prediction, a pattern-based technique utilizing local weighted learning is suggested. 25. A summary of the most recent advancements in autonomous vehicle architecture is made in the research work. 26. Despite the fact that some individuals may seem to be suspicious about the practical application of autonomous driving, AD, as a kind of replacement for current cars, the abundance of research and trials being carried out indicates the contrary. Automated vehicle researchers and organizations are developing effective tools and strategies. An extensive investigation of the design methodologies for smarter frameworks and tools for AI and IoT-based automated driving was performed in this study. 27. Additionally, its implications encompass the functionality of automated electric vehicles. In this article, several nations and organizations' actual driverless truck, car, bus, shuttle, rover, helicopter, and subterranean vehicle implementations are explored. While academic robotics research shifts from using internal mobile systems by means of full-scale means of transportation with high stages of automation, the automobile industry is undergoing a shift at the same time. The motor systems of modern vehicles have changed, making them easier to handle by computers. They also now have various sensors for navigational purposes, and they have nodes in vast communication networks. The most are. That is the heart of artificial intelligence for autonomous vehicles. If it helped, a quick subscribe keeps more summaries coming. So how do autonomous and vehicles connect? That is exactly where we started. Go back to the top and watch it click into place.